Mark, tell us what actually does happen. Not that I don't think Brigitte could, just to give us all a little airtime.
So of course, it's kind of wild. The place where you would least expect to see something on that screen is exactly behind that big barrier that's in the middle.
Yep.
And somehow, when you actually do the experiment, you see that actually that's where most of the particles end up. So it's almost exactly the opposite. And then you get this weird pattern with other bands going out. And so you initially would stare at it and shake your head and wonder what you'd actually
So we'll analyze what that means in just a moment. But we often, I don't know, probably almost everyone in this audience has seen a still image or an animation like this in the discussion of quantum mechanics. And I thought it would be kind of nice to show you that this actually happens. It's not just animation that an artist does. So we're going to actually do the double slit experiment for real right now. And to do that, I'm going to invite a friend of mine from Princeton University, Omelan. Can you wheel out, if you would, the double slit experiment? All right, so what we have here is a laser on this far side. So this is our source. So actually we're doing this in some sense opposite to the orientation that we saw in the animation. And we're going to fire this laser, which is photons in essence. And the photons are going to go through a barrier that has two openings in it. It's harder to see that, of course, mechanically. But trust me, there's a barrier with two openings. And we're going to take a look at the data that falls on a detector screen, which in the modern age is a more complicated and somewhat finicky piece of equipment. So we're all sitting here on spilkas. If you speak any Yiddish, you know exactly what I'm talking about right there. But hopefully this will work out. So Oman, why don't we just actually see ambient noise? Can we see a little bit of that first? So can we switch over to the input to the screen? All right, so this is the output from that device. And now if we actually turn on the laser and allow us to collect all of the photons that land, there they're building up. And there you see what actually happens. So this is the result of this very device here. And you see it. We have you can see on the very far left, we see some of the photons are landing. Then we get a dark region in between, then a bright, a dark, a bright, a dark, a bright, a dark, and a bright, and a dark, even though this device over here really is a barrier that has only two slits in it. So the animation that we showed you actually does hold true in real experiments, and that then forces us to come to grips with it, to try to understand what in the heck is actually going on. So thank you, Omelan. So there we have it. We have this situation in which we expect to get two bands and we got more. What does that tell us? Where do we go from there?
There's an existing bit of mathematics that comes up with exactly that same pattern, but it has nothing to do with particles. It's the mathematics that you use to describe waves, water waves, or other kinds of waves.
Yeah, so can we see the animation that has a single? So this is a warm-up to the problem where we have water going through a single opening. And just tell us what we see happening here.
That's right. So you've got sort of a water wave, a wave front coming along, and then just that slit acts as a bit of a source for this rippling wave going out in a circular pattern. And you see it's most wavy at the place behind the slit, so the wall. I think that's indicated by the brightness there.
Yep. And then if we go on to a more relevant version for the actual double slit experiment.
Yeah. So now we've got that same wavefront, but now there's two slits, and it's like there's two different sources of waves. Like if you threw two different pebbles in the pond at the same time, and then what happens is that you're both creating waviness, but some places on the screen, the wave from one is doing this, and the wave from the other is doing this, and they kind of cancel out. But right there in the middle, what's happening is that the wave from the one slit is going up right when the wave from the other slit is going up, and then they do this, and you get a big wave, and that's the bright part. But if you work out the mathematics, then the places that have the big waves are exactly these bright ones, and that's just like we saw in the double slit
Right.
for the particles.